Interference is one of the most discussed topics in Wi-Fi. But since you can't see interference visually, it's hard to track down, and sources of interference are all around you. In the fourth installment of our Wi-Fi Air Expert series, we'll discuss various sources of Wi-Fi interference and how they affect the signal. By definition, interference is any unwanted RF signal that disrupts Wi-Fi's normal operation. The impact of that interference can range from lowered data speeds to complete signal loss, depending on the nature and severity of the source of the interference. The two primary sources of interference you're likely to encounter are other nearby Wi-Fi networks and interference from other devices. The most important thing to remember is that the Wi-Fi RF channel is a shared medium, which means that all devices connected on the same channel as your access point will be sharing the same bandwidth. Each device only transmits packets of data when no other device is transmitting. To achieve this, there's a built-in Wi-Fi detection mechanism called Carrier Sense Multiple Access with Collision Avoidance, or CSMA-CA for short. Wi-Fi devices use something called Carrier Sense to detect RF activity on the channel. If a device happens to be in the middle of a transmission, the others will wait until the channel is free. You can think of it like a room full of very polite people where everyone is waiting for their turn to speak, but how much they can communicate is regulated by the number of people waiting to talk. In the case of Wi-Fi, the available bandwidth is effectively divided by the number of devices attempting to transmit at any given time. Now imagine that your closest neighbor's access point is configured to the same RF channel as your own. In that case, not only do your own devices share available bandwidth, but all of the devices that are within range have to share. And by range, it means that their signal's strength is strong enough to be detected by your devices. This will trigger the CSMA-CA mechanism to stop transmission if it detects activity, regardless of whether the originator is within your own network or your neighbor's network. To follow that previous analogy, that room full of polite people has now doubled in size, and half of them aren't even in your party. Everyone still waits their turn to speak, but they'll have to wait even longer. This phenomenon is called co-channel interference, or CCI for short. Now imagine that your nearest neighbor's access point is configured to a different RF channel. In the 2.4 GHz frequency band, the channels use a 20 MHz wide spectrum, but adjacent channels are only separated by 5 MHz. So if the two access points in our example are configured on channels 1 and 3, their frequency spectrum has significant overlap, which creates interference. The data transmission of both networks will be affected. This time, think of two adjacent conference rooms, also full of very polite people. Everyone still waits for their turn to speak in each room, but the noise from the adjacent room occasionally disrupts the conversation in the other. The louder the noise from the adjacent conference room, the more the speaker will have to repeat himself to be fully understood by his own audience. This phenomenon is called adjacent channel interference, or ACI for short. Now let's look at what happens when the chosen frequency channel spectrums do not overlap. For example, one access point is still using channel 1, but the other is using channel 6 instead of 3. The data transmission within the two wireless networks will be completely independent, and both will have optimal performance. To continue the conference room analogy, it's like adding a thick brick wall between the two conference rooms. They can now independently communicate within their own group without interfering with the other. Now that we've covered Wi-Fi related sources of interference, co-channel and adjacent channel interference, let's talk about non-Wi-Fi sources. When the FCC opened up the 2.4 GHz RF spectrum for non-regulated use, the Wi-Fi 802.11 standard wasn't the only one jumping on the opportunity. Numerous other devices also communicate on this frequency band without adhering to the 802.11 standard. A few very common examples are baby monitors, cordless phones, wireless cameras, wireless audio devices, Bluetooth devices, security systems, and microwave ovens. All of these devices constitute sources of non-Wi-Fi interference. They emit signals in the 2.4 GHz band either on a single frequency like Zigbee, or continuously emit across the entire spectrum like a microwave oven. These interferers don't follow the 802.11 protocol rules, so influence can start while Wi-Fi devices are in the middle of a transmission and last for an unknown duration. Non-Wi-Fi interference feels like sitting in a room full of loud and unruly people, but you're still trying to be polite and wait for your turn to speak. In this environment, the destination will often receive the transmission with errors and require that they be retransmitted. In some cases, it will attempt to continue operation in the presence of non-Wi-Fi interference by automatically switching to a lower data rate, which slows down wireless applications. And in the worst case, if the interference source is strong and constant, the Wi-Fi devices will simply withhold communication until the interfering signal goes away. Okay, time for a quiz. Which source of interference is the worst? Co-channel interference, adjacent channel interference, or non-Wi-Fi interference? Well, of course, all sources of interference are bad, but non-Wi-Fi sources don't obey the 802.11 rules, making them hard to track down unless you have a dedicated spectrum analyzer to detect them. This makes them the worst of the three kinds of interference.